So welcome back. What did we just do? The diagonalization proof shows that it's impossible to align the real numbers, that's the decimal numbers, with the natural numbers. Even if you take a subset of the real numbers. So you might think, okay, if I just take the numbers between 0 and 1, I should be able to align those with the natural numbers. But it turns out it's impossible, and that's what the diagonalization argument shows you. And no matter what mapping you try, I tried one mapping, but no matter what mapping you try, the diagonalization argument kicks in and shows you that there are dogs, a very large number of Zoggian dogs who get no collar at all. And this rather contrived thing about dogs actually shows you that the set of all the real numbers is a larger infinite set than the set of natural numbers. So the set of natural numbers, think of it a bit like this. There's 0, then there's 1, then there's 2, and basically it's a bit like there are discrete values all the way along. 0, 1, 2, discrete values. The real numbers are a bit like a rainbow. It's a smear, a continuum of values, and that's the difference between the sets, and that's how we get the difference between the sets that we saw. So these two sets have very different properties. You can do proof by induction on the natural numbers. You can't do it on the real numbers. So the set of natural numbers is called a countable infinite set. It's not a great name. Listable would be better because you can start listing them. 0, 1, 2, 3. And the set of real numbers is called an uncountable infinite set. And we use the name cardinality to talk about the sets. So the countable infinite numbers, that's cardinality 0. And the uncountable real numbers, the real numbers are in cardinality 1. So they're a step up in terms of their size. So this brings us on to the idea of thinking about how we can classify sets. Well, in fact, there are, to start with, there's the distinction between finite sets and infinite sets. And that's easy enough. A finite set obeys the following property. If I list all the members of the set, I will eventually stop. It might take a very, very, very long time. It might be a huge set, a massive set, like the set of all grains of sand in the Sahara Desert. That's a massive set, but it's finite. You will eventually stop. So here's the set of the odd numbers which are greater than 0 and less than 1,000. 135, quite a big set, but it is finite. An infinite set is one where if I try to list all the members of the set, I will never ever stop. Never. There's always a next one, in other words. So the set of all the odd numbers greater than 1,000, well, that starts at 1,001, but it goes on forever. One of the interesting things about that set is that although you look at that set and you think, well, that's a subset of the natural numbers, it does in fact have exactly the same cardinality. In other words, it's exactly the same set, it's exactly the same size. And that's a little bit counterintuitive. But that's the way that infinite sets work, because at one end, or certainly for the natural numbers, at one end they're unbounded. That means that you can line them up all the way along and you can show that they are essentially the same set and have the same properties. Now, if you've got an infinite set, as I've already shown you now, you may have a countable set. That's one that you can align with the natural numbers. That's a nice small infinity. It's a well-behaved infinity. Countable infinite sets we can align with the natural numbers, like, for example, the dogs that have strings for names, Fido and Odie and all of that stuff. All the strings of the MIU system, all of the theorems of the MIU system, that's another good example of a countable infinite set. You can just, because they're strings taken from a finite alphabet, you can just turn them into numbers very easily. Now, an uncountable infinite set is one where you can't align it with the natural numbers. You try to make a mapping and you fall on your face. You can't do it. In other words, you get a proof by contradiction, which is what the diagonalization argument is. The set of all the real numbers is an uncountable infinite set. Uncountable infinite sets are in some sense bigger than the countable infinite sets, in the sense that if you try to make a mapping, you will find that there are some elements left over, just as I did with the collars and the real numbers, the dogs that were from the planet Zog. So here's a diagram, a kind of class diagram, that shows you what types of sets exist. Sets are either finite or they are infinite. And the infinite sets are either countable, that means that you can align them with the natural numbers using an algorithm, or they are uncountable. Uncountable means if you try to do a mapping between the set and the natural numbers, you will find that you can't do it. And that's things like the real numbers. So finally, after 7 and a bit weeks of toil and trouble, we are now ready to do the proof that there are such things as non-computable functions. And you understand the words in this statement now. If P is the set of all computer programs, you know what computer programs are, you've written some. And F is the set of all functions which map N onto M, and N and M are members of the set of natural numbers, N. Then the next bit says the size of F. These bars mean that's the size of F. And it's really here talking about the cardinality of this set. The size of F is greater than the size of P, and therefore the set of functions mapping natural numbers onto natural numbers is bigger than the set of all computer programs, and therefore there are some functions in the set of all functions for which no computer program can exist, and therefore there are such things as non-computable functions. So first of all, in this, let's think about how big is the set of all the programs that they are. Well, computer programs are just strings. They're just strings of characters. You type them at your keyboard using a text editor, and they're just strings. Carriage returns, that's just another character. So when you get to the end of the line, you hit carriage return. Carriage return is just another ASCII character. So you can think of a computer program just as a very big long string. And it's a string where the characters of the string are taken from a finite alphabet. They're just like the dog names. Obviously, most computer programs are longer than the name of a dog, but they are finite strings. Even a computer program with tens of thousands of lines of code, it's a finite string, and it can be turned into a natural number using exactly the same numbering scheme. Another way of thinking about this, if you don't like the argument about strings, well, if you don't like the argument about strings, I'll just say accept it, it's true. But another way of thinking about it is that you know that all computer programs just get turned into binary, zeros and ones. So when you take your computer program and you compile it, it turns into a binary executable. Well, any binary string is clearly a natural number because I can just convert that into an integer. It is an integer, it's expressed using ones and zeros. So what that tells me, both of those arguments tell me that the set of all computer programs is infinite, because I can always write a new computer program, just add some extra code on the end, but it is countable. The computer programs are essentially integers. Okay, so each and every computer program can be expressed as an integer. So there are no more computer programs than there are in the set of natural numbers. And I think you can see where this is going. how big is the set of all functions? Right, so now we're going back to the idea of functions as potato diagrams. But in my potatoes now, I've got two infinite sets. The domain of my function here is the set of natural numbers, 0, 1, 2. Those are the inputs. And the codomain of my function is also the set of the natural numbers, 0, 1, 2. And that defines how many, that defines all the possible computer programs I'd like to write. I put in a natural number, I get out a natural number. So for example here is a function which maps natural numbers onto natural numbers. Now you can see for this one, I've simply chosen the function that maps n onto n squared. That's a computable function. Why is it computable? Because I can put an algorithm in place, an algorithm being a computable procedure. You know, you can write it down and give it to your friend and they can do it. That's what an algorithm is. So there's an algorithm that can compute this function for me. The question I want to answer now is, how many different possible functions are there that take one of these as inputs and give one of these as outputs? In other words, if you think of a potato diagram as a wiring diagram, how many different ways are there of wiring this up? So 0 onto 0, 0 onto 1, 0 onto 0, 1 onto 1, 2 onto 2, 3 onto 3. That's one way of wiring it up, not very interesting. 0 onto 0, 1 onto 1, 2 onto 4, 3 onto 9. That's another way of wiring it up. So I've got two ways. How many different ways are there of wiring this thing up? And can I align all the possible functions with the natural numbers? So just as before, I'm going to try to align all the functions for you. And again, I'm going to do it on my piece of paper on my desk. So I'll see you in a minute.